Good afternoon, everybody. Welcome to the last session of the first day of SLE. I'm Adrian Johnstone, in case any of you have forgotten in the last 2 hours. This last session involves models of two kinds. The first two papers are about modeling the software engineering discipline, and the third paper is about large language models, which is completely different, but somehow they've all ended up in a session on modeling. Our first speaker is Weixing Zhang, and you're ready to go. The floor is yours.
Okay, thank you. Good afternoon, everyone. My name is Weixing Zhang. I'm a PhD student from the University of Gothenburg and the Chalmers University of Technology. And I'm also very happy to introduce my co-authors, Regina Hebig, who is a professor from the University of Rostock in Germany, and Daniel works in the same university as me, and he is my PhD supervisor. And Jan-Philipp was also a professor in University of Gothenburg, and now he is working for Xitaso in Germany. Our paper is about automated extraction of grammar optimization Lua configurations for metamodel-grammar co-evolution. There are two directions of co-evolution. We can migrate metamodels according to the changes to the grammar, and we can also migrate the grammar because of the changes to the metamodel. And here, our paper is about migrate the grammar when the metamodel changes. Let's take a look at these two pictures. These are two programs expressing the same contents, but they look very different. Why is that? Because they are confirmed to different grammar. The left one confirmed to the grammar which is generated from the metamodel, and the right one confirmed to the grammar created by an expert, even though the two grammar adhere to the same abstract syntax, but the programs of these two grammar still look so different. And the left one was what we got in a project. But why did we generate grammar from metamodel? The story of the project was years ago that we wanted to explore blended modeling technology in that project. And as a start, we developed a textual language for EASL-ADL. EASL-ADL is a metamodel-based DSL, which used and it is architecture description language which used in automotive embedded system domain. And because it is a metamodel-based language, and the metamodel is already there, so we can generate the grammar from it instead of designing grammar from scratch. And such a metamodel-driven way is also very suited for blended modeling. And by the way, what is blended modeling? Here is a scratch map for that. For example, in a language, there are multiple concrete syntax. They are confirmed to the same one abstract syntax, and they interact with each other seamlessly. And it is allowed to have some inconsistencies between the concrete syntax. And then let's go back to the problem. This, as I said, this is what we got by generating from the metamodel, and we program according to that grammar. And this is a program. It looks very ugly because you see the nesting is very deep, and there are lots of keywords and braces. Most of them are unnecessary. But why is that? As I said, it confirms to the grammar because grammar defines that. In the generated grammar, there are lots of things, for example, keywords, braces, commas, and many things that we want to remove or modify. So did our industrial partner. They also want to have a nice textual grammar. So then, when we really try to optimize it, we find further issue. For example, here we remove the keyword short name, and we want to also move the attribute short name exactly after the main keyword. This is aligned with our program habit. And the problem is that there are lots of grammar rules also have the same attribute called short name, and that means we should do the repeated modification of many grammar rules. So we want to automate it instead of manually work. And there are lots of other types of modification. For example, we want to change the orders of the attribute. For example, we want to remove the optionality. So we also think maybe there should be a method that can use for other languages. So we need a general modification rules. And we also sort of a question: what if the metamodel evolves? Maybe some languages evolves very fast. We need support to the evolution. So based on the issues, we developed a tool called the Grammar Optimizer. Maybe the name is not that good, but we call it Grammar Optimizer. And this tool take the generated grammar as the input and optimize it to be a nice one or to an expert created one. And it's based on many general rules for optimizing the grammar. And how to use these optimization rules, we have configure to invoke the public method of those rules. And here is an example of the configuration. We can see here it's about 22 lines of configurations, but it optimizes thousands of lines of text in the grammar text. And then it's about the goal of this paper. We sort of a scenario that a metamodel is co-involved with an associated grammar. Here is a script map. We can see that first we have a previous version of a metamodel. We call it M1 here, and it evolves to another version of a metamodel called M2. And there is a grammar called G1, which is generated from the metamodel. And we did some manual improvements to make it more concise or to more beautiful and get G1 prime. And now the requirements comes. We want to make sure that the grammar still align with the metamodel, the involved metamodel. So we generated the grammar from the metamodel again. We got G2. And another requirement is that we want to have the manual improvements in the grammar. But we cannot just copy it. So we can use the grammar optimizer to do this. But the problem is that, as I said, we need to configure the tool. So the method here is to we compare the generated grammar and the optimized grammar for the first version, and to extract the configurations And we will use the configuration to drive the grammar optimizer to optimize the generated grammar, that is G2 here. And the extraction work is done by the tool configure generator. So how to do the work? The whole process of this methodology is that in the first step, we select some sample languages, and then we obtain the targeted grammar and the metamodels of these languages. And then we develop the tool, we call the tool configure generator. We developed this tool according to the principle of the grammar optimizer, because the lower configurations anyway will be used in the grammar optimizer. And then in the evaluation stage, we generate grammars from the metamodel by using Xtext. Then from now, the generated grammar and the targeted grammar are all in place. So it's time to apply the configure generator. The configure generator takes these two grammar as the input and output the optimization lure configurations. And then let's go into the assessment. The idea is that we use the configurations to drive the grammar optimizer to optimize the grammar, to get an optimized grammar. So then we compare the target grammar and the optimized grammar to see whether they are the same or they are different, or how many grammar lures are different. So how do we implement the configure generator? I wouldn't go too much deeper here, but I will go through simply. In the first step, we read the text of the grammar, and then we split the grammar into grammar lures and put each grammar lure into a data structure, and then we connect all the data structure as a list. So there will be two lists. One list is for the generated grammar and another list for target grammar. So then we traverse one list to fetch one grammar lure at a time. And we search for a grammar lure with the same name from another list. If we don't find it, that means there should be an optimization lure for removing the grammar lure in the configurations. If we found it, then we can just compare these two grammar lure. And this compare based on the line matching and line comparison. Then we identify the differences and generate the required lure configuration. And after that, we also check if there is any new grammar lure added. So then we complete the calculation of required optimization lure configuration. So then we write the optimization lure configuration back to a file. That's what we got, and this will be used in grammar optimizer. And here is a simple example of how the extraction works. For example, there is a line of an attribute from the definition of a grammar. The attribute is called an owned comment, and the left one is from the generated grammar, and the right one is from the target grammar. And we compare them, and to identify the different. For example, in the owned comment in the generated grammar, there is a keyword called owned comment, but there is no such keyword in the right one. So here we got to know that there is an optimization lure called a remove keyword is needed. So this is how, and here we apply the regular expression to identify the differences. And finally, we go to the results. There are many columns, but the most important is the right three columns. But here I also go through other columns. In the second column, it shows the lines of configuration that manually made configuration. And the third column shows the line number of the extracted Lua configurations. We can see that the extracted optimization Lua configurations have more lines than the manual one. And from 4 to 6, we show the how many grammar rules should be changed or removed or add when comparing the target grammar to the generated grammar. And from 7 to 9, it is the result of comparing the optimized grammar to the generated grammar. It shows how many grammar rules have been changed, how many grammars have been removed and added. And finally, we compare the target grammar and the optimized grammar. And the result shows that there are three languages: SLE, EDL, BibTeX, and XNet have the same grammar rules in both optimized grammar and target grammar. But there are some grammar rules different in the optimized grammar and the target grammar for the three languages: DO, TX, Core, and SML. So there is some grammar rules are different. So there should be something missing. So what are missing and why they are missing? First, the line order sometimes matters. There would be some adaptation and modification change to the line order, then it will affect the calculation. And the second is a grouping of attributes is unprocessable for the moment because, as I said, our comparison is based on line by line matching and comparison. And if there is some capability that are missing in the grammar optimizer, then we cannot extract any Lua configurations for that because, as I said, the configuration, the configure generator is according to the grammar optimizer. And if there are many, for example, optionality in a same line, it will also confuse the comparison for the moment. And why it is still useful? Because this tool can help us to we don't need to start from scratch, even if we don't extract all the required Lua configurations. You can continue that. And the speed is important. It still reduces a lot of time. And the conclusion of the future work, the conclusion is that the proposed method for the automatically extracting grammar optimization rules, which capture manual improvements from a previous evolution step and allow these improvements to be replayed in the future versions of grammar. Future work. First, we want to improve the coverage. As the previous page shows that some coverage still hadn't been 100%. So one idea is that we can move to our work to abstract syntax tree. Yeah. And we also want to do some work on the complementary co-evolution scenario. That means migrations of a metamodel after changes to the grammar. And then we also want to apply the approach to a practical environment because so far the evaluation is based on some sample languages. And we are also thinking of the creation of a language workbench that supports blended modeling. So the proposed method will also contribute to that. Yeah, and so thank you.
Thank you, and commendably to time. Do we have any questions? Could you come and use the mic because we're live streaming? Thank you.
Thank you very much for your talk. My question is that in the slide where it was like problem statement, you mentioned the configuration rules. So is configuration an input or is it something that you generate? And if it's something that you generate, do you have the initial grammar and the optimized grammar available so that you can generate configuration? Is that clear?
I'm not sure if I fully understand the question, but I can try to answer. The generation is that we have already many existing optimization rules which was developed in our previous work. That is the tool called a grammar optimizer. So then in this generation, we actually is to calculate what is needed, what is the needed optimization rules is. So with the calculated rule configuration still need to find the rules from our previous work. That is 60 optimization rules. So the generation is actually to match what the rules needed.
Right. So if I repeat what you said is you already have that grammar optimizer from your previous work, so you generate configuration based on the optimized grammar that you have.
Yes.
Okay. Right.
Yeah.
Thank you.
Thank you.
Okay, thanks. Eric.
Hi, thanks for your interesting talk. I was curious if you could maybe characterize the kind of rules in your previous work in the optimizer and how those rules are different than the ones you're extracting from the manual rewriting. Are they sort of fundamentally different looking rules, or?
Could you repeat your question?
If I understood right, you have the existing rules in the grammar optimizer.
Yes.
And then this work is about extracting more rules from the manually fixed grammar.
Yes,
right. And so how are the rules different? Are they similar, or are the ones you extract like specialized versions of the general ones, or?
Yeah, the rules they are similar, but they are different. They works for different modification purpose. But yeah, from the implementation level, they are similar.
Yeah, maybe I could ask you later, but I'd be curious to see like in examples of the different rules, if they're
okay.
Like, why did the general ones not fully solve the problem, and you needed to extract these additional ones? So,
I think that the optimization rules, we can freely combine different optimization rules from the whole set of the rules, and to do different modification. And it is very general, and we can apply it to many languages. But what I said, the coverage is not reached. In some languages, the coverage is not reached 100%. Is just about the generation.
So you get more coverage with the extra rules.
Yes.
Oh, okay. Okay. Cool. Thanks.
Okay. Any more questions? Well, let's thank the speaker again in the usual way.